If you strip apart an old portable radio, you'll find a black loudspeaker driver like this. Inside it is a piece of metal that produces a continuous, invisible pulling force, a magnet. That exact same pushing and pulling force works on a much larger scale too. Inside the massive generators powered by rushing rivers like this one, giant magnets spin to produce the electricity that powers entire cities. Whether it is pulling a dropped sewing needle out of the dirt or running a national power grid, harnessing this invisible force starts with mapping exactly how it works. This diagram separates common materials based on a common myth, the idea that magnets stick to all metals. They don't. Materials like copper, aluminum, and wood are completely unaffected by magnets. To get an attraction, you need specific metals: iron, steel, cobalt, or nickel. When these specific metals are permanently magnetized, they develop two distinct ends, which we call the north and south poles. These poles are where the magnetic force is at its strongest. These poles follow a strict rule, known as the law of magnetism. Opposite poles, north and south, will pull together and attract. But if you try to force two matching or like poles together, they will push away and repel each other. Memorizing those four specific magnetic metals and that strict rule of attraction and repulsion is the foundation for testing how magnets behave in the real world. Sprinkling iron filings around a magnet reveals its invisible field. We map this with vector lines. The force always travels out from the North Pole and curves into the south. Lines never cross and pack tightly at the poles, showing where the pole is strongest. Drawing these lines gives us a precise mathematical map showing exactly where the magnetic force exists and how strong it is in any given spot. Suppose you have two identical steel bars. Sliding bar A toward bar B causes attraction, which doesn't confirm which is the magnet. Flip bar A around. If they repel each other, both are magnets. Repulsion is the only definitive test. Trusting repulsion over attraction prevents false positives, letting you quickly distinguish a true magnet from ordinary scrap metal. That permanent magnetic structure isn't indestructible. You can destroy a magnet's invisible field by dropping it in a hot charcoal stove or violently hammering it. Look at the microscopic structure of a magnet. It gets its force from billions of perfectly aligned internal particles. Intense heat or physical impacts cause these particles to vibrate violently, scattering them into random chaotic directions and erasing the magnetic field. Predict the field lines between two repelling north poles. Solution: lines exit both north poles and travel towards each other. Since they can't cross, they push outward, leaving an empty center gap. This neutral point is where magnetic forces cancel out completely. Whether you are looking at scattered internal particles or disrupted external field lines, a permanent magnet only functions when its structure remains perfectly aligned. We rely on that perfect structural alignment to navigate. When mariners cross wide, featureless bodies of water, they use instruments to track the magnetic fields around them. The needle inside a compass is simply a tiny, lightweight, freely suspended magnet. It automatically spins until its north pole lines up with the Earth's geographic north. But this creates a paradox. We know that opposite magnetic poles attract. If the north pole of our compass needle is pulled toward the top of the globe, the Earth's geographic north must actually be acting as a giant magnetic south pole. To find your way on the surface, you have to trust the massive, inverted magnetic structure churning deep inside the Earth. Grab a screenshot of this summary table. To predict how a magnet will behave, remember that only iron, steel, cobalt, and nickel are naturally magnetic. The field lines around them always flow outward from the North Pole and curve into the South Pole. The law of magnetism dictates that like poles repel and opposite poles attract. And because attraction can happen with any plain piece of steel, repulsion is your only absolute proof that you are holding a true magnet. By learning the rules that map these invisible forces, you can solve complex physics problems on an exam or navigate safely across the largest lakes and oceans.